Our next speaker is Mattias Ohlsson, who will be telling us about machine learning techniques for medical applications. Please.
Thank you. It's a very broad title, which gives me a lot of freedom to talk about what I want. I just found this graph from a review. It's about publications that uses deep learning in health informatics. And you can see this trend that has been going on now and is still going on, that around 2015 something happened. And deep learning became really popular in a lot of fields, and also in medical related fields. A lot of things happen in imaging, for instance. So for me, that do a lot of machine learning, and especially in medical application, this is really exciting times. So I'm going to talk about a few techniques that we have been developing in a specific area of machine learning in medicine, in survival analysis, but I'll just briefly mention a little bit of what you're dealing with when you work with medical data in comparison to other fields. For instance, the concept of truth is really tricky in medical applications. So we call it gold standard. But it's really a struggle of having a correct label to things. And labels are also quite expensive. Again, and also sizes of databases. That could be a real issue in medical applications. Sometimes we work with cohorts where we have only hundreds of patients, comparing to where you work with images, where you have millions of images. So sizes of database can be an issue. Also, if you want to use the machine learning in a clinical setting, things like interpretation of response and feedback requirements can be really important. You need to the doctor that is going to use the black box doesn't really like the concept of black box and really wants to have a feedback. These are, I would say, mainly unsolved things for machine learning, especially for deep learning algorithms. And missing data, but you have heard missing data a couple of times. I won't go into that. I'm going to give you a small example to start with to point out some of the difficulties that may arise. So this concerns machine learning and small data sizes. So an example, suppose I have a data set with 100 patients, and for each patient I have 150 measurements. We can, each patient has a binary label, for instance, good or bad. And the task, find a subset of measurements that is important for the classification problem of separating good and bad. And let me give you an example where I have data of this size. We are working with immunotechnology here in Lund, and they have a protein chip where they can measure protein content from, for instance, blood. Typically around 400-ish proteins can be measured. The content of proteins, for instance, from blood. And then you try to relate that content to medical questions like, does this patient have pancreatic cancer? Is there a risk of relapse or recurrence of cancer and things like that? So the data you have are really similar to the example I showed you here. Order of 100 patients, more measurements than typically patients. I can start with such a data set. I can, for instance, take a linear model. It could be logistic regressions, linear support vector machines, a simple perceptron if we want to use neural networks. And I can train repeatedly and remove low-performing variables or proteins. And I can start out with my 150 proteins, and I can see I measure performance in something called area under the curve. 1 is good, 0.5 is bad. And I can see that it doesn't make sense to have 150 variables, but something happens here when I remove variables. And at some point, around 20 to 40 variables, or I see that I have really good performance. And you start to think, okay, have I found a signature here? Something that a small subset of these proteins that is very much related to a medical question. But all this is rubbish. And we can call it the curse of dimensionality or anything. Because what I actually did here was I had a data set with randomly generated, normally distributed variables, along with random good and bad labels. So out of 150 dimensional data, hundreds of them I can by random find a really good signature. But it's all random. This is what you face when you work with medical data, where you have a lot of measurements, small data cohorts. You can easily fool yourself if you do it the wrong way. The problem here is called overtraining, and because I repeatedly use this training data set for a lot of decisions along the way, and I cannot do that. The solution is called validation, validation, validation. 95% of my time when I work with small data cohorts, I spend that on validation, validating your model. It's not particularly tricky, but it can be time-consuming. And you have to do a lot of looping here and there. And for every time you make a decision based on a data set, you need to validate that decision. And then you can work things out. So that is my little, the take-home message here in my little example is that when you work with medical data sets, with machine learning, it doesn't have to be complicated machine learning. This was a linear method, is to be really careful with validation and avoid overtraining. What I would like to talk about now is a couple of techniques for analyzing survival data. So survival data, what is that? It's typically when you have data where you have a pattern at some point. So it could be that you have a transplantation going on, and you have a pattern, and the pattern here is, if we talk about patients, just the characteristics of what happened at that point. Patient, how did the patient look like? Measurements, blood measurements, everything. So you have a pattern of that patient. And then, at some point, we have an event. It could be death. It could be relapse of cancer or anything. Yeah, typically, there's a lot of deaths here. And what you want to do, you want to correlate that pattern with the event, where you have time. So survival analyzes time duration until an event occurs. There is a slight complication with that kind of data. It's called sensor data. It could be the fact that here, at some point, a patient is dropping out of the study. We don't know what happened with it. We only know that it didn't have that particular event, at least up to that point, but then we don't know anything more. Or if we have a end time, the current date, and some patient didn't have the event, well, it's a censored event. So what do we do with these? A very common thing is to look at the survival function to see how the probability of event as a function of time. So you can try to model this survival function, or you can try to model something called the hazard function, which has to do with event rate. This is common, so I can try, so if I have a big cohort, I could try to model this one. can I build a machine learning model that can actually predict individual survival curves for individual patients? But it's also quite common in these data sets to define risk scores. So instead of trying to predict event time, which turns out to, in most medical data sets, is notoriously difficult, to have a model that actually predicts the event time is typically extremely difficult. So instead you build risk scores with the aim of being able to sort a cohort according to event time. So you do that a lot. Sort patients according to risk. And sometimes if you can sort them well, you can also define risk groups. Let's say that I want to have a high risk group and a low risk group. That can also be important clinically. If I sort, then I would like to measure how well am I doing sorting. And there is a index called C-index, concordance index. It's a measure of how good I can produce such a risk score. In principle, it has to do with how well can I sort patients according to event time. So if I have a risk score with a very high risk score, it means that that patient has a high probability of having an event in a short time. So high risk score, low event time, short event time. And you just measure with what this C-index, just measure how well am I able to sort patients if I compare it to the event time. In presence of sensor data, so you have to take that into account, that sometimes you really don't know what happened with a particular patient up to a certain point. I don't have to go into details how you do that, but that C-index is taking that into account. So that's one thing. Another thing is to define risk groups, as I said. So, and here is an example of 3 risk groups. So here is a low risk group and a high risk group, if we look at the survival function for these different groups. And there's a middle one here. So if I have a high risk group, and if I know that you belong to a high risk group, well, then you can take measures. So when it comes to survival modeling, to model the survival function or hazard function, then there are standard models. A lot of these standard models are based on what is called Cox proportional hazards, Cox models, or extension of Cox models. But you can also find other machine learning methods based on neural networks. And you can take, if you take a neural network, you can always make it deep. So you call it deep learning models for survival analysis. There is something called random survival forests. So you can do random forests in a survival context. But this is for mostly modeling the survival function itself. What I'm going to talk a little bit about now is something that we worked with a couple of years ago, namely to use neural networks to actually optimize C-index and define risk groups. So the task, construct a risk score that maximizes the C-index. And a risk score is just a number. So I have my patient characteristics that I feed into some model, and out comes a number which is my risk score. High score, high probability of an event. This, if you're into the neural network business, you would identify this as a one hidden layer neural network. So I can construct a neural network, and the purpose of that neural network is just to output a number. But I would like that number then to give me a high C-index if I compare the number with the actual event times that I have in a training data set. So I would like to maximize this C-index. Again, if you're into the machine learning business, you typically, when you want to train a model, you want to construct an error measure, and then you want to do gradient descent-based learning, so you want to differentiate the error function. This is tricky when it comes to a measure like this, because this has to do with sorting and ranks, so it's tricky to differentiate. So the way we solve that is to train these networks in order to maximize the C-index using genetic algorithms, which is one of these techniques that you can use where you don't have, when you don't have access to when you can't compute gradients, basically. It works okay. It's something that it takes a little bit more time to train than gradient descent-based methods. Naturally, I have less information in genetic algorithms, but they are quite universal. So we tried that, and it worked out quite well. This was an application, so we had a task in mind. It was looking at, we had a breast cancer data set, and the event was distance recurrence of cancer after primary diagnosis. So you have had cancer, and then at some point you have a relapse. And so this is, again, a survival analysis technique. With our score, we were able to at least provide a very low-risk group in this case, better than with other techniques. So that was one example. So if I go back here and say, sort according patients to risk, so you have a risk score. What is typically done anyway with that risk score is to define risk groups. So if I have a risk score, I can put a cut on the risk score and say if you are above that cut, you are high risk group, or you are low risk group. So if you're going to do that, why don't we do that directly? So why don't we say the task is now to find high and low risk groups without any risk scores? So we bypass the fact of actually defining a risk score. We say, let's see if we can have a model that can predict patients and put them into two groups. So here's an example. Another example. Again, very small data sets on the order of hundreds. This is low risk and this is higher risk. So that what we want to do here is, again, use a neural network to predict group membership. And what do we want to optimize here? Well, let's optimize what is called here, these are the survival curves. It's called Kaplan-Meier estimates of the survival curves if you have groups of data. So this is the low risk group, and this is the Kaplan-Meier estimate for that one. This is the high risk group, Kaplan-Meier estimate for that one. Let's say that what we want to maximize is the area under the survival curve for low risk groups. So I want that to be as much in the top as possible. And I want to minimize the area under the survival curve for high risk group, because that is the group that should, if I put it bluntly, die off as fast as possible. Again, this kind of optimization is tricky to differentiate, because it's the way of going from the area here back to the neural network is tricky. So I cannot use gradient descent based method. So again, we rely on having techniques training techniques on genetic algorithms. So this is the flow chart we set up. We have training inputs. We use the neural network to predict group members. We do the Kaplan-Meier estimate. We compute areas, and then you can have constraints so that we have some constraints on the group sizes. And if it's a high risk, then we have some fitness measure. If it's a low risk, we have the reverse fitness measure. So we use that, and we use a genetic algorithm for training this. And the interesting thing here is that if I have a network for doing the group membership prediction, I have very much freedom how complex I can have that model. It can be a very simple linear model. I can make it more complex. I can even go deep and talk about deep learning, because I can make the model really deep. And I can have images, whatever. And just a small example here. We tested this on various medical data sets and compared with other methods. And of course, in this example, our method turned out to be the winner. So these are a couple of techniques not taken directly from a machine learning library, a little bit of invention, but it has to do with machine learning and analyzing survival data. Yes, I'm actually pretty much done. Again, as I said, it's interesting years ahead. There is a lot of going on in the machine learning community, especially with deep learning in all aspects of working with medical data. So I think it's going to be very interesting. And we're going to hear in the after lunch more focused on images, for instance, and medical data. Thank you.
Thank you very much, Mattias. Okay, question and a reminder that you should speak into the microphone, although it won't make you louder, because you will then be recorded.
Now, I was thinking about where you maximize the order thing, where you had sort of one SI over larger than SJ.
Yeah.
Would it be possible to relax it? It's sort of binary, but I mean classification problems are also binary, but they're made into a gradient descent learning method by sort of softening that and so that you actually get a gradient. Is that an alternative?
That is actually something that is proposed, yes.
Okay.
So you can do that, or you can define lower maximal bounds on measurements, and you can use these bounds and optimize them, and then you have in a sense relaxed them so that you can use gradient descent basement. Yes.
Because it seems so popular now to try to get it end-to-end learnable.
Yeah.
To try to devise it so that you can use a gradient descent method from.
So one of the methods that were tested here was based on that, yes. But we wanted to do our idea was actually to do the full thing. Yeah.
Thank you, Mattias. Very interesting. What is this genetic algorithm for training? What is it about?
So it's about so you have your network and you have your weights, and when you want to train a network like this using genetic algorithms, you have your fitness measure. That is what you want to maximize typically. And what you do here, you can do mutations. So you and crossover. So you can change this network. So this weight may be changed with that weight. So you make a whole new network. And then you can, of course, typically what is going also that this network is changed a little bit. So you do these modifications that you typically do in genetic algorithms, crossover mutations. So you change the network. And if it doesn't work out, well, it's discarded. But if it gives you a little bit higher fitness measure, well, you keep on working with that. So you work with a population of networks and you modify them according to rules. And eventually, and the ones that are high performing, they are the ones that are kept there. The ones that are low performing, they are dying out.
Okay, if there are no more questions, let's thank Mattias again.